Good afternoon, class. Today we are going to continue talking about Chapter 4. So let's do a little bit of review. What is an isotope? You may remember from the previous lecture that an isotope are atoms of the same element that have the same number of protons and electrons, but different numbers of neutrons. So let's take a look at the following elements. Which of the pairs below are isotopes of the same element? And in part 2, in which of the pairs below do both atoms have 8 neutrons? Well, first, let's determine which of the pairs below are isotopes of the same element. Remember, we are looking for two atoms that have the same number of protons, but differing numbers of neutrons. These numbers up here at the top are the mass number, which tells you the mass number is equal to the number of protons plus the number of neutrons. Right? This doesn't help us because we're looking for the same number of protons. The number on the bottom is the atomic number. The atomic number tells us the number of protons. So we are looking for a pair that have two of the same atomic number. Alright, so let's erase this so we can see a little bit clearer. Which two pairs have the same atomic number? Pair 1, you have an 8 and a 7. Not the same. Pair 2, you have a 6 and a 6. The same. And pair 3, you have a 7 and an 8. So the pair that contains isotopes of the same element must be pair B. In pair B, both elements have 6 protons. But the first one of pair B has 6 neutrons. The second one has 8 neutrons. How did I get 6 and 8? Again, remember that the mass number is the number of protons plus the number of neutrons. So to determine the number of neutrons, you take the mass number and subtract the number of protons. 12 minus 6 is 6. 14 minus 6 is 8. So pair B are isotopes of the same element. How about part 2? In which of the pairs below do both atoms have 8 neutrons? Well, what do we have? 15 minus 8 is 7 neutrons. 15 minus 7 is 8 neutrons. So that rules out pair A. In pair B, we already said we have 6 neutrons and 8 neutrons, so that rules out pair B. In pair C, we have 15 minus 7 is 8, and 16 minus 8 is 8. Both of these elements have 8 neutrons. So for part 2, pair B, both atoms have 8 neutrons. Let's talk a little bit more about isotopes. Magnesium has 3 naturally occurring isotopes. The average atomic mass of magnesium is 24.31 atomic mass units. So again, this is the number that you find on the periodic table. It is the weighted average of all naturally occurring isotopes of that element. And it is the number on the periodic table below the chemical symbol. Okay, so again, weighted average. Does anybody know what weighted average means? A weighted average not only tells you the average mass, but it gives you an idea of how much of each one are that mass. So chlorine has 2 naturally occurring isotopes. The atomic mass is 35.45. How did we find this? Well, to calculate atomic mass, you use the experimental, meaning what we found in the lab, percent abundance of each isotope of the element. We multiply this by the atomic mass of that isotope, and then we sum across all isotopes. So what does this look like? Again, the average atomic mass, we're going to take the percent abundance, we're going to write it as a fraction, and multiply by the isotopic mass. What does percent abundance as a fraction look like? Remember that percents are all out of 100. So to write the percent abundance as a fractional abundance, we simply take the percent abundance and divide by 100. Okay? Again, the fractional abundance is the percent abundance written as a fraction. So we take the mass of the isotope, multiply by its abundance in fraction form. Then you take the mass of the second isotope, multiply by its abundance in fraction form, and the third element, multiply by its abundance in fraction form. Then you add up all of these values to determine the average mass. In the case of magnesium, we get 18.88 for the magnesium 24, 2.531 for magnesium 25, and 2.902 for magnesium 26. Adding all of this together, we get 24.31. Let's take a look at our periodic table for a second. Lithium only has two naturally occurring isotopes, lithium-6 and lithium-7. Let's take a look at what the average atomic mass of lithium is. Per our periodic table, it is 6.94 atomic mass units. Is this closer to 6 or closer to 7? Since it is much closer or higher, closer to 7, we can say that the lithium-7 is the most prevalent isotope. If this value was closer to 6, then we would say that lithium-6 is more prevalent. Again, this is a weighted mass, meaning that the average atomic mass also tells you a little bit of information about how much of each one you have. Let's look at gallium. Gallium is an element found in lasers used in CD players. In a sample of gallium, there is 60.10% of gallium-69. Gallium-69 has an atomic mass of 68.926. Gallium-71 is 39.9% of the sample. It has an atomic mass of 70.925. What is the average atomic mass of gallium? Again, we're going to take the mass, 68.926, and multiply that by the percent abundance as a fraction. So 60.10 divided by 100. If we put this into our calculator, we get 68.926 times 60.10 divided by 100. Please remember when using your calculator to use, if you're putting it in an all-in-one string, to use the appropriate parentheses. This equals 41.425. The second piece, gallium-71, has a mass of 70.925 atomic mass units times the fractional abundance, which is the percent abundance over 100. Right? Again, if we put this in our calculator, 70.925 times parentheses 39.90 divided by 100, end parentheses, the second piece is 28.299. Now, if we add these two things together, .425, we get an average atomic mass of 69.724. Now, is this number closer to 69 or 71? Well, I would say this is closer to 69, which makes sense since 60% of this element is gallium-69. Only 40% of it is gallium-71. Let's talk about electromagnetic radiation. We can experience electromagnetic radiation in many different forms, including light, the colors of the rainbow, or X-rays. Electromagnetic radiation consists of energy particles that move in the form of waves. The distance between the peaks of the waves is called the wavelength. So again, if you're measuring the length of a wave, you measure from the top of one wave to the top of the next, not from what you think is the bottom to the bottom, from what you think is the start to the bottom of the next peak. Again, we measure wavelength from peak to peak. High energy radiation has short wavelengths. Low energy radiation has long wavelengths. This is important. high energy, short wavelengths, low energy, long wavelengths. When you take an element and heat it up, and then take light from that and pass it through a prism, as is illustrated here, it separates into distinct lines of color, separated by dark areas. We call this an atomic spectrum. Every element has its own unique atomic spectrum. The lines in this atomic spectrum are associated with the change in energies of the electron. In an atom, each electron present has a specific energy known as its energy level, which is assigned a principal quantum number. Principal quantum numbers are whole numbers starting with 1, i.e. 1, 2, 3, 4, etc. They increase in energy as the value of n increases, meaning 2 has a higher energy than 1, 3 a higher energy than 2, and so on. The further the electron is from the nucleus, the larger the value of n and the higher the energy. The energy of an electron is something we call quantized, meaning electrons can only have specific energy values. Right? Not every energy value is possible for every electron. You can think of this like a bookshelf. If you have a bookshelf, you can only place your books on certain levels. There is no level 1.5 or level 3/4 or level 2.6, right? Your books can be on level 1, level 2, level 3, level 4, or level 5. When electrons move to a higher energy level, they absorb energy to do so. When they fall back down to their original position, they emit light or give off light. Emit is just a fancy word for give off light or give off. The energy emitted or absorbed is equal to the differences between the two energy levels. It is the arrangement of electrons in an atom that determines the physical and chemical properties of each element. Each energy level has one or more sublevels. The number of sublevels in an energy level is equal to the principal quantum number n of that energy level. The sublevels are identified as S, P, D, and F. The order within an energy level is S first, S being the lowest, then P, then D, and then finally the highest being an F level. On level 1, n equals 1, you can only have one sublevel. The first sublevel is S. So for n equals 1, you have 1s. For n equals 2, you can have two sublevels, an S and a P on the second level. On the third level, you can have three sublevels, an S, a P, and a D. On the fourth level, you can have four sublevels, S, P, D, and F. Where an electron is described in terms of probability. We don't know exactly where an electron is, but we can assign probables, meaning we think the electron is in this space, or it is likely to be in this space. Orbitals are just a three-dimensional space where we were most likely to find an electron. S orbitals look like spheres. The higher the level, the larger the sphere, the further away you are from the nucleus. There are three p orbitals starting on level 2. Each p orbital has two lobes, kind of like a balloon tied in the middle, or a dumbbell shape. Each p orbital can hold 2 electrons, maximum. The three p orbitals are arranged perpendicular to each other around the x, y, and z axes, meaning you have a p orbital horizontal, one vertical, and one coming in and out, coming out towards you from the computer and in towards me. D orbitals, 4 of the 5 look like 4 lobes, or 2 p's tied in the middle. They are aligned along or between different axes. The 5th d orbital looks like a p orbital with a donut around the middle. Like a p orbital with a donut around the middle. Each d orbital can hold a maximum of 2 electrons. There are 5 of them, so each d can hold up to 10 electrons. The Pauli exclusion principle states that each orbital can hold a maximum of 2 electrons. Therefore, an s can hold 2, Each p can hold 2. There are 3 p's, therefore you can have 6. Right? So an s can hold up to 2. There are 3 p's. Each p can hold 2 for a total of 6. Each d can hold 2, and there are 5 d's. So each d can hold 10. And f's, there are 7 f's. Each f can hold 2. Right? So 2 times 7 is 14. Okay? Electrons within the same orbital, meaning the two that are sharing a space, repel each other. They don't want to be very close to each other if they can avoid it. They must also be spinning in opposite directions, i.e. spinning clockwise or counterclockwise. Right? They must also, if they're within the same orbital, they must be spinning in opposite directions. We represent these magnetic spins with arrows, up and down, showing opposite spins. So there is a maximum number of electrons that can fill each sublevel, 2 for the S, 6 for the P, 10 for the D, and 14 for the F. Electron configurations follow the order of occupied sublevels on the periodic table. We will be talking about this in a separate supplemental lesson. There is a table in D2L called the Electron Configuration Table. Please have that table out when you pull up that lesson. This concludes Chapter 4, Part 2. Thank you for listening.